Hi everyone, I am Sumbul. Today I will present one of our recent works for simultaneous remote sensing image compression and indexing for efficient image retrieval. This work has been done together with Xiang, Nimisha Madam and Begüm Demir at Remote Sensing Image Analysis Group of TU Berlin and has been supported by ERC Grant Award. Considering the growth of remote sensing image archives, scalable and accurate image retrieval that aims to find similar images for a given query has been an important topic in remote sensing. It is worth mentioning that remote sensing images are usually stored in a compressed format to reduce their storage size in large-scale archives. Accordingly, image decoding prior to any remote sensing image retrieval method is required. However, this is a computationally expensive operation, so that impractical for large-scale image retrieval problems. Accordingly, in this work, we aim to achieve image retrieval in a scalable way while eliminating the need for decoding remote sensing images prior to retrieval. Based on this, we introduce a joint framework that simultaneously applies remote sensing image compression and indexing through hashing. While doing so, we aim to compress each image to a minimum length bit stream with a minimum amount of distortion and at the same time obtain discriminative hash codes. We also aim to learn compatible image latents for both compression and indexing. Here you can see the illustration of the proposed framework. There are two main modules. First module accepts a remote sensing image, compresses and then decompresses back with a deep neural network based encoder-decoder. Second module generates hash codes based on the image latents coming from the first module. I will explain each module in the upcoming slides. First module compresses remote sensing images while minimizing the length of bit stream and the amount of distortion. To this end, this module employs a pair of encoder-decoder for learning to reconstruct remote sensing images, an entropy model for reducing the length of bit streams. Accordingly, this module includes three main blocks. Image encoding block maps a remote sensing image with its latent, which is quantized with a rounding function. Compression decoding block maps the resulting quantized representation into the reconstructed image. Entropy modeling block estimates the actual distribution of image latents with an entropy model. Arithmetic encoder and arithmetic decoder algorithms are applied on the quantized representation to generate bit streams. For entropy model, we consider context-adaptive hyperparameter-based Gaussian mixture model since it has been found promising for spatial redundancy reduction. Image compression objective can be defined according to the rate distortion optimization problem, where a rate term is cross entropy between the entropy model and marginal distribution, and distortion term is multi-scale structural similarity index. This objective requires to apply computationally demanding research of lambda parameter for different rate distortion points. In the upcoming slides, I will explain how our framework automatically finds a variable range of rate distortion points. It is worth noting that this module is independent from the image compression method and can operate with other encoder-decoder architectures. Hashing-based indexing have attracted attention for scalable image retrieval due to its high time efficient and accurate search capability within huge image archives. Accordingly, this module indexes remote sensing images through discriminative hash codes, which are obtained from the latent representations of images already characterized in the first module. Before giving the details, let me first explain you hashing-based indexing. You can see its illustration in this slide. It maps high-dimensional image features into compact binary hash codes that are indexed in a hash table. Then image retrieval can be achieved by returning the similar images from the hash bucket having the same hash code with a query image. To achieve it, this module includes three main blocks. Index decoding block extracts indexing specific image embeddings with an attention layer followed by convolutional layers. Class prediction block maps image embeddings into class predictions with a fully connected layer. Hashcode generation block maps embeddings into k-bit hash codes, again with an FC layer. To learn discriminative hash codes, we utilize three loss functions for this module. Soft pairwise loss allows to model ranking among semantic pairwise similarities by considering soft and hard similarities. Bit balancing loss allows to learn hash codes with a balanced distribution of 0 and 1s by maximizing their variance. By classification loss, discriminative capability of hash codes are further enhanced. Then the objective for this module is composed of weighted combination of these losses. To train our framework, one could directly optimize the aggregation of all the considered losses. However, different objectives can enforce to encode different information on image latents. This can lead to the competition between objectives or the dominance of one of the objectives. Accordingly, learning image latents compatible for both compression and indexing, while automatically weighting different losses and finding a variable range of rate distortion trade-off points is important. To this end, we introduce a multi-stage learning procedure with 3 stages. In the first stage, only distortion loss from the compression objective is optimized to ensure the reconstruction capability. In the second stage, all the losses for compression objective is optimized with multiple gradient descent algorithm that allow us to automatically find a variable range of optimum rate distortion trade-off points. In the third stage, indexing-related losses are included in the learning process, while their weights are automatically found by PC graph technique. Let me give you the experimental results. For the experiments, we use the big ArcNet images occurred over Serbia that includes almost 15,000 images. Their pixel size for 10-meter band is 120 by 120. For other bands, we applied bicubic interpolation. Each image is annotated by multiple classes from 19 distinct classes. You can see the parameters selected based on a cross-validation strategy. We compare the first module with JPEG 2000 algorithm and RNN-based state-of-the-art compression method. We compare the second module with the standard indexing on fully decompressed data that doesn't involve joint learning of compression and indexing. We also compare the multi-stage learning procedure with the standard learning procedure for simultaneous compression and indexing that only optimizes the aggregation of all the considered losses. In this slide, you can see the MSSIM results at different bits per pixel values. First module provides the highest result at each BBP value. This shows the effectiveness of the first module compared to RNN-based method and JPEG 2000 algorithm. In this slide, you can see the mean average precision results at different bits per pixel values and also retrieval time. The retrieval accuracies obtained by the second module are very similar to those obtained by standard indexing. However, our retrieval time is significantly less than that of standard indexing, because standard indexing includes decoding of all archive images, which is not needed by our framework. This is an important advantage, especially for image retrieval applications operating on large-scale image archives. In this table, you can see the compression and retrieval performance of our framework and standard learning procedure for joint learning of compression and indexing. At similar BBP values, our framework provides significantly higher MSSIM, precision, and recall values. This shows the effectiveness of our multi-stage learning procedure for both compression and indexing accuracy. In addition, standard learning procedure requires computationally demanding research and multiple trainings to find a variable range of rate distortion trade-off points that is not required by our framework. In this work, we introduce a novel joint framework for simultaneous remote sensing image indexing and compression for scalable image retrieval applications. Our framework eliminates the need for image decoding prior to image retrieval without losing from compression and retrieval performances. And it achieves scalable image retrieval thanks to its effective hashing-based indexing. By the proposed multi-stage learning procedure, it is able to learn image latents compatible for both image indexing and compression. As a feature work, we plan to integrate 3D convolutional layers to the image encoder block of our framework. This is the end of my presentation. Thank you for listening to me. I will be happy to hear your questions.